Hi, passing scientists. My name is Jorge, and today we're going to discuss a problem that is already solved in the book I'm gonna provide you with in the description. But I had to bring it to you. I found it really interesting. So let's get into it. We have three snails located at the three vertices of this triangle, and we are asked for the time the snails take to meet each other in the centroid, right? And also the distance they cover during this trajectory, right? So let's discuss this part of the problem, because after we are asked about finding the equation of this path, but that's the second part of this problem. Let's get into the first one. And right, we have to find out the time and the distance covered, and to do so, let's decompose this vector into a vector that goes straight to the centroid and a vector that is tangential, a tangential velocity vector. First of all, let's find out the tangential velocity vector. And to do so, let's discuss basic trigonometry. We know that the angle here is 60 degrees because it's equilateral triangle, and the half is 30. So we just have to find out the sine of 30 equals to, yeah, right, we all understand that. We all understand this. And the velocity, the tangential velocity, is the half of the velocity vector right here. Right, so now let's find out with the same method the velocity straight to the point. With the same method, okay, we have the velocity straight to the point is this factor multiplied by the velocity that we already know because the exercise provides us with the number, so we just have to plug into the number, and we just have the value of this velocity vector straight to the point. So now that we have the velocity straight to the point, we just have to find out the space straight to the point in order to find out the time that the snail take to meet each other, or what is the same, to reach this centroid, right? But firstly, we have to find out this distance. How? Right? We just have to find out this position vector from this vertex, because I chose this vertex for convenience. And, no problem, I could have chosen this one or this one, but anyway. And we just have to find out this position vector, and we know that this distance is 60 centimeters. The exercise also provides us with this number, and we just have to do another time trigonometry. But as you can see, it's not difficult. You just have to apply basic geometry from high school, basically. And alright, we just have to plug in, and we just have to find out this position vector, right? And if we plug in, we get this number. And after we have this quantity, right, that is this one, we just have to plug into this kinematic equation, and we just have to find out the time, right? So dividing this term by the velocity straight to the point that we already know that is this term, right? As you can see, we divided here. You got the 8 minutes. And once you know the time, you just have to apply another time the kinematic equation in order to find out the distance covered, right? And the velocity. As all we know, the value is 5, and as the velocity is constant, doesn't change, we don't have to care about if it's going to change in time. No, it's constant. So as we already know the time, we just have to plug in and get the number. As you can see, it's not difficult. We just have to apply basic geometry. And now let's find out the equation of the path that, as many of you will know already, is about the spiral logarithmic path or trajectory, right? So let's discuss this equation using a drawing or a draw, right? We have this. Let's say that this point is the centroid of our equilateral triangle, and let's say that we have this position vector straight, and this is one of the vertex of our triangle, and we have this angle, this phi angle, and this is the trajectory. This is the spiral, right? A path of the spiral. A piece of spiral. And talking about pieces, if you take a small or an infinitesimal piece of the trajectory, you get that you have a line. So I just exaggerated it because like that we can see it clearly, right? With clarity. And we have this triangle, which has an angle that doesn't change, okay? In this case, we had p divided by 6, or 30 degrees. I mean, we have this 30 degrees that, even though we have a spiral, and this snail is moving with a spiral until it reaches the centroid. Sorry, you're not watching anything. Sorry. So here, I was talking about that the snail is following a spiral until it reaches the centroid, and this angle, even though this snail is going through a spiral, this angle doesn't change. Okay, it's always 30 degrees, and this is what it's representing right here. But okay, but this angle, right? That it's the vertex of, or it's the angle that we have in the opposite vertex, is changing and it's increasing, right? So we have this angle, and in time it increases. But what happens with this position vector, this r prime I call it, that after an infinitesimal piece of time, it just shortens. Okay, it shortens, and that means that this, if you want to find out this piece, right, you just have to do a differentiation between the initial vector, that is r prime, you have it, and the final position, that is r. So final minus initial position vector, you got the difference right here. I think that's clear. Just I want to clarify everything. And what happens with this? We just have to do some just trigonometric relationship, and we got this one. This set is this part of the triangle, and we just have to. We all know that with the sine of a small angle, or a sine of a small angle, is the angle, that small angle. So we just find out the z, that it's this, alright? And now we could use tangent, this relationship, or this relationship. For convenience, as you'll see, we'll use this one, because we want to get an equation analog to this radioactive decay equation that we just have to keep in mind, because as you can see, we can get an equation that is totally analog to this one, just doing a little bit of algebra. And I just wrote down the solution already, because I don't want to get too long in this video. So as you can see, we have the solution already. We already have the solution, and we just I just did a little bit of algebra. As you can see, everything is clear, and once we are here, we can clearly see that those are analogs. And once right here, just we do the same process, and we have already got this equation that is the equation of the path that this exercise asked us for. Alright, so thank you for watching and stay tuned, more videos are coming. Bye.